do you have to download or just
Yep. Let me finish this. Support vector machine. Yeah, you can see. SVM. Now SVM. Well, what's the general idea of SVM? Any idea? Another algorithm. Support vector machine. Yeah, you're correct. Last week and last week we talked about the linear regression and logistic regression. What's the beginning point of linear regression and logistic regression? How we derive the objective? In linear regression, what's the objective?
We need to find B0 and B1.
Minimize.
Oh, yeah.
Minimize what?
Cost function.
Cost function. What's the cost function?
Cost function is mean root square error.
Yeah, kind of mean, not root square, mean square error. This is prediction. This is true, ground truth. Do square, then to minimize over the sample data. Okay, so all good. How we derive this? Okay, let's do the logistic regression. What's the cost function, objective function for logistic regression? Actually, it's not only for logistic regression. It can be used for any classification model. What's that? Minimize what? Recap? No one remember? Minimize negative y log y high. This is prediction. This is ground truth. Minus y minus y log y minus y height. Yep. How we derive this to objective function? We're using probability theory. Which theory we use?
Okay, I found this on the web for which area you use. Check it out.
Not theory. Theory.
Bayes theorem?
Sorry?
The theorem we use was Bayes theorem.
Bayes theorem. We use Bayes theorem to transform the original form of the probability to what? To likelihood. So the theorem is called MLE. What's MLE? Remember? Maximum what? Likelihood estimation, right? That's how we derive this. What we care about is about the distribution of y. Then we derive this to objective. For this, what's the distribution of this y? Remember?
Normal.
Yep, normal distribution. For this, what's this? Distribution for this? Sorry. I.
I think it was Bernoulli.
Yep. Correct. Thank you for the answer. All good. So this is also can be applied for in week 10. We will finally achieve the neural network. This framework also applies for neural network. But now we need to deviate from this theories. We need to go to a geometric theory. Not theory, geometric, always geometry is something more intuitive. So geometric intuition to find an algorithm. This algorithm is called SVM. So now, do you have any idea what's the geometric intuition we use to come up with SVM? No MLE today, but we will go back to MLE. And if you are machine learning engineer, deep learning engineer, AI engineer, you will come up across MLE in your whole career. But Now I will take some niche area. This area I will talk about the algorithm today. Maybe you will never use it in the future, but just talk about it. Especially if you work on big data. If you work on the small data, you may still use the SVM, Simple Vector Machine. SVM. Think about what's the geometric intuition we use. So I will draw the geometric graph to explain. No, I need black color. What's geometric? Geometric is that we just project all the data points on the feature map. So this is feature 2, this is feature 1. So we draw some points, negative point and positive point is binary classification task. We always start from binary classification. Then we can generalize binary classification to multi-class classification. Do you know how to generalize to multi-class classification? I give you, I always think you are very good at, abbreviation. So let me give you abbreviation. OVR. What's OVR? One versus rest. That means you have two classes, 1, 2, 3. You choose one, then put the other two together. Now it's binary. So the question is this belong to the class 1? Yes or no? Is this belong to class 2? Yes or no? Is this belong to class 3? Yes or no? So now we have we turn multi-class classification into binary classification. So always begin from the binary classification. We have some point. This is a negative point. We have some, let me call it positive point. Positive plus. We have some negative point. Is negative minus. So for geometric, what we want to do? We want to draw a line. We want to make a line to separate the negative and negative and positive. So next time new point come in, we can say if it belong below this line, it's positive. If it up this line, is negative. So good. So we need to figure out this line. So which line we want? Let me give you two lines. One line is like this. Another line is like this. This called line 1. This called line 2. Which one you choose? Line 2. Okay. Line 2, 1 volt. Anyone choose line 1? No, line 1? 0. So how about other people? Line 2, 3. Okay. I assume all of you choose line 2. No other choice? Nope. Can you explain it? Good research paper always come from the, verbal language. Can you explain it intuitively? Why you choose line 1 instead of line 2? SVM from the paper from Wapnick. This paper is very, very significant. I think Wapnick became a professor mostly because of this paper, maybe. So can you have the same intuition as Napnik? Napnik always draw this is that, okay, line 2 seems to be more reasonable, but he can explain it. He explained it first. Then he found it first. Then he explained it intuitively. 3, he applied his mathematical knowledge to find this line. So that's how you make an academic paper. So now let's do 2. You see line 2, why?
It looks like the graph we have seen.
Look like.
Same as the graph we have seen on the lecture.
Okay, so you even do the step 1. Okay, so now let's go to the intuition idea, why the line 2 is more intuitive. If you choose line 1, if I add another positive point, is it reasonable to be here? Right? But it's reasonable to be here. But if you have this line, you have a misclassification. So what's the idea of line 2? The idea of line 2 is, what do you want? You have the maximum margin according to your existing data points. What's the maximum margin? The maximum margin is like, okay, think about it, it's like a street. Then you want to move these straight lines upwards and go down. So what's the maximum point you can move to without misclassifying any training examples? Is this line? Is this line? So what they said is, okay, look at this margin. This is margin. He wants this margin to be as big as possible. So let's look at this line 1. What's the margin? For this positive example, this is the best you can do because there is a positive point here. What's the best you can do for the negative point? There is negative point here. So if you move, you come across negative point, you have to stop here. So let's look at the 2 margin. This is first margin for line 1. This is second margin for line 2. This margin is bigger, so we choose this one. Make sense? This is intuitive idea of support vector machine. All good for this? Let me remove the line 1. We only focus on line 2 to figure out how we can mathematically find line 2. Then we finish. Okay, that's it, clear. So the objective would be maximize the margin. So I don't know margin, but what we want to know, what's the parameters here? What's the parameters? We want to find the line. If we want to find the line, what would be the parameters from this line?
So what if we minimize the distance between one positive and negative?
That is our projective. But what's the remember in linear regression we have y equal to beta x plus beta 0. This is parameter we want to change. This is parameter we need. But how about this? What's the parameter for this? For this line? This is a line. It's similar to this. This is also a line, right? But this is a line between feature and label. This is a line for the feature itself. So what is this? W what? Transpose X. Actually, just it's same as this. If you take this as Y, if you take this as X, what would be this line? This line would be W1x, you minus put y this sign, plus it's this line, right? It's any line, right? Actually, we have some, here I can put the some beta 0 here, because if I divide by beta 0, here is beta 1, beta 0 x, here is 1, beta 0, y, plus y equal to 0. So here it's just a random, just random number, it doesn't matter. So what is here? It's just wx1 plus w2x2, maybe some shift, intercept. So we have maybe b here equal to 0. You say transpose. Why is transpose? Because we can take it as a vector form. It's w1, w2, transpose x1, x2. So now we have transpose. So, but anyway, what's parameters now? What we want to achieve? W1, W2, and B, right? So, okay, just use just make it simple. W transpose x plus b equal to 0. And we want to find W and B. Then this W and B will maximize this margin, right? Okay, so let's do it. Let's find what's the goal here? If we make this margin into a function about the W and B, then it's solved. Why? There are a lot of optimization algorithms can be used for solve this projective. One is gradient descent we used last week, right? If not convex, doesn't matter. You have some solution to find the global minimum, trying to find the global minimum. Yep, so let's do that. Let's make margin expressed in the form of W and B. How we can do that? Firstly, let's find these two lines. So let's define these two lines. These two lines they're parallel and it's also symmetric according to this line, right? So we can derive this. We can derive these two lines. Define this line as W transpose x plus b. Okay, let me make the decision rule first. We will look at these two lines later. Let's look at this one line. One way we will set the example. If I give you one example, xi, can you tell me when we can set xi belong to negative class? We put xi here. So if I say it's negative, it should be what? Less than 0. If it's a positive, xi plus b should be less than 0, okay? So now I want to consider these two lines rather than only consider this one line. I want to say if it's below this line, it would be it would be what? It would be positive. If it's up these two lines, if this upper this blue line, it will be negative, right? So rather than if this is 0, so we can say this is maybe large equal than 1, right? If this is less than 0, if we go for this line, it's down below this one, so it should be less equal to minus 1. I just define some value here. You know, it can be 2, it can be 3, right? Now, in the original paper, the author defined it as 1, so I also put 1 here. Okay, so now we have this. Still remember, what's our goal? Our goal is to represent this margin in the form of W and B. So let's see whether this can help us. Okay, what's the margin here? Okay, let's look at the margin formula. Now we have, you know, when this line stops here, it's because we have a positive point on this line. We can just move down further, right? So now we can look at this one. This is vector for this point. I call it x plus. Oh, this is make a circle for that. Also, same thing. We have x minus here. Then what I want to do is I want to find this vector. This vector is perpendicular to these 3 lines. What's this vector? Do you know that? This is W transpose x plus b. Then I want to find a vector perpendicular to this line. What would be this line?
Its slope would be,
Yep.
their slope product would be minus 1. So we can calculate the equation from there.
You calculate what?
For example, this line's slope and this line's slope, their product would be minus 1, and it's passing through origin. We can write the equation for this line.
Their product will be minus 1. Actually, if you find a point, if you find this vector, and if you find this vector, if they are perpendicular to each other, these two vectors, the product is not 1, it's 0.
0,
Yeah, it should be 0, right?
yeah.
You are correct. So we need to find a vector to make this vector and this vector, the product become 0.
Yeah.
The dot product become 0. Let me find it. Actually, I directly give you answer, then prove that. That would be easier for me. The answer is W transpose. It's just W. You know, it's just W here. This W would be perpendicular to this. So I will prove using, you know, these truths. So how I can prove that? I found 2 points on this line. Point 1, I call it Z1. Point 2, I call it Z2. So Z2 and Z1 on this line, right? So what's the vector for one vector for this line? One vector will be Z1 minus Z2, right? So Z1 minus Z2, so then you have this vector, right? So you have this vector, then you have this form. What you can do is you can W transform Z1. I just do the whole work. W transpose Z2 plus B. You have B here, you have B here, you have minus here, so you eliminate this. So what you have W here, and you have Z1 times Z minus is minus Z2. You have this. Remember, this is equal to 0, right? Because it's on this line. This also equal to 0 because it's on this line, right? So 0 minus 0 is 0, right? So W transpose this is 0, right? That means W vector is perpendicular to this Z1, Z2. Z1, Z2 is this vector on this line, right? So now we know we can find that W here is perpendicular to this. This is true. W is perpendicular. Okay, so now we can calculate margin. How we can calculate margin? If we know this vector and we know this vector, and then we also know this vector. We can calculate margin, right? How we can calculate that?
For example, let's we have equation of this line which is perpendicular to the
Which
both
line? This line?
Yeah,
Yep.
perpendicular to the both line. So we can get to the point at which it is intersecting the parallel lines.
Intersect this parallel line.
Yeah, and other one.
This one.
Yeah, this one.
Yep.
Dotted one.
Positive or negative?
Yeah.
Yep.
lines.
Both line. Then
Yeah, and we calculate the distance between those 2 points.
on this line.
Yeah.
Yep. That's true. So what you want to do is you want to project this vector on this line first. You want to project this vector on this line. So then you calculate the distance between these two, right? You're right. So if you project it here, if you project it here, then this would be exactly the margin, correct? Now we do the projection. How we do the projection? We use dot product, right? As we said, I think in PCA, right? In PCA, we also do the projection on the eigenvector. So we do the same thing. Wx transpose plus minus W. Let me. Would it see this? Yeah, it can see that. Transpose x minus. This would be margin. Is that margin? Actually, we miss one thing. Sorry? No, that's okay. If we do have parameter b, that's okay. But now we don't have parameter b here. Remember, we don't this is not on this line, so we don't calculate the something for this line. We'll calculate the point on this line. Yeah, so we don't need b here. Okay, so it's not correct. It's not totally correct. Why? Because this W is not in unique length. Remember, this just perpendicular, but it's not in unique length. It means its length is not 1. So we want to make it to length 1. So we will divide it by the length. Yeah, correct. W. This would be margin. Okay. So now our goal is to maximize this. Okay, so if can we solve this? We can solve this. Look at here. If for this positive point on this line, this is this line. So this WT. So according to this, WT transpose x plus b would be equal to 1. Oh, sorry, it's on this, so it would be minus 1. So this is plus, right? For this. And for this, we have WTX. Why I have something like this? Plus b equal to 1. Okay, So now we can eliminate this. What's this? Is I put this on this side. Minus b. What is this? Right? So this is, oh, actually we should, this is bigger than this. So we should use, this x minus this. Plus. Okay, so y minus is here. Y minus is here. Plus b minus is wait a minute. I have some. It shouldn't be. Let me revise this. This is plus b. This is plus b. Have a look. It's not correct. This is plus b, then equal minus this. This is for this, correct. This is for this, correct. Less than 0 equal to 0. And then this one would be 1 minus b, 1 minus b. This one would be, okay, let me do this. I think it's correct. Here is minus b, minus b, so we can eliminate, right? And 1 minus 1 equal to 2. So what we have is this, right? Yeah, this is correct. Oh, good. So finally, we have this in terms w and b. Actually, we don't need b. This is good news. This is our final things. So I think we finished this. This red color. Yeah, but I can't erase this because how we get this is under the constraint of this. So we need this constraint. So let's unify these two constraints. So that's two binary classification. So if it's positive, y, we assume y is 1. If it's negative, we assume y equal to -1, or good. So now we can unify these two. We can see if it's positive, we put y here, it doesn't matter. Same thing. It's also large, right? If it's negative, I put -1 here. That's b. Here is also multiplied by -1. It's become 1, but now the less than become larger than, right? So now we unify them. Rather than these two, we only need this one constraint. This is good for. So now we have this optimization problem with constraint yi times wtxi plus b large equal than 1. Okay. Anyone good at mathematics? Not mathematics. Anyone good at the linear programming or quadratic programming? How we can solve this? With we can solve a quadratic function if without constraint, but now we have constraint. How we can solve this? Anyone know that? Actually, I don't plan to do the Lagrangian multiplier from the scratch. So normally you don't do that. You look for a mathematician to do that. So no worries. The thing is, I want you know there is a thing called Lagrangian multiplier. You can eliminate this. Eliminate this, but we need to make some change on this. How we change that? Alpha. This is sometimes we call this is multipliers. So what's the form of this? Yi x w transpose xi plus b minus 1 here. Sorry, let me leave this term here. Don't combine it here. Normally, what you want to do is you want to first step make this to minimization form rather than maximization. As I said last week, we always do that. So if we want to maximize this, it's equal to minimize this, right? So now we add this form. Now we can equal to minimize square then minus this. If you want to add this multiplier to the maximization, you have to put this minus 2 plus. Never mind. It's for this is final form of support vector machine. Now, how you can solve that? You have to look at some mathematician or mathematics student to find a solution for general quadratic programming. I'm not an expert for that, so if you give me this, you want me to solve that, I will use gradient descent. So that's it. Let me think about that. It's not practical, so I only show you code how to implement that, because I can implement, I can do the derivative to get beta 0 and beta 1 directly, so I can implement it directly. I can implement gradient descent directly because it's just, it's just a form of update of parameter equal to W alpha. Then you have derivative. That's easy. But here, I cannot do that. Implement from scratch. So what you can do is, as always, use sklearn, SVC, something like this. But still, I have some practical thing to show you for tuning the model, because one important thing, I think you already get some feeling if you get touch on the algorithm really using your mind, because some students don't use their mind. They don't think about whether my algorithm good or not. So what I mean is you should feel like sometimes the training performance is good, but the test data, performance on test data doesn't good. It's not good enough. If you look at your assignment last week, you will get on every start site the classification result for training data is like 89, something like this. But for your test set, you maybe get this. This is actually good enough, but if you plan to do a D task of HT task, it's very important. If you plan to become a machine learning algorithm, it's also important. You can't forget all of this algorithm. The only thing you need to know is how to balance this. This is actually good, but how about the test data accuracy become 57? What's the terminology for this scenario? Overfitting. Yeah, we call it overfitting. How about something like this? What's the scenario for this?
Underfitting.
Underfitting, right? You have to recognize this, so you can tune your hyperparameters. So how you can in something like just in something like this, how you can deal with this overfitting in your logistic regression model? Regularization. Yep. Can you be more specific? All of algorithm, if you want to tune for this, we call it regularization. But in logistic regression, what's the parameters we want to tune to add some regularization? Sorry? Uh-huh. Penalty? Penalty. What's that? Penalty. It's just another word for regularization. Sorry? Theta? You use theta as penalty. now it's become the very concrete answer. Yep. If you remember I think maximum likelihood, just take any maximum likelihood. For regression is where there's something like this. What you want to add? Okay, just add theta. Actually, in our case, it's beta 1 and beta 0. The only thing we want to clear is beta 1. So we want to penalize this beta 1. We want to penalize using this theta for penalty. Why it work? Why it work? Any intuition for why it work? I explained it, I think, last week. Why we penalize it, it will work. Remember what's the maximum likelihood we derive from this? It's P, we derive from the Bayes theorem, P x y, and we have a P x, let's use y, y theta, P theta. We have some constant here, we don't care about the constant. Last week and last week, what I want to solve is this term, but we never solve this term. So the thing is, we don't want to, if you solve for this term, you just look at the training data. What I want to do is, okay, I want my training data become as accurate as possible. You see, I have a theta, so I want what's the probability of x, y become maximized? We want to maximize this, right? So what we care about is our training data. But what you should care about, another thing you should care about is theta, is parameter. So now, let's say your parameter is like, okay, I have a distribution for my parameter. You know, it's probability of parameter. Normally, I have a normal distribution, center around 0. It's like, it's more possible if your parameter is around 0. That means it's small. The absolute values are small. So if it's less, if it's far away from 0, it's very big. The absolute values are very big. It's less probable. So you can see, that's what we do here. We want to minimize that. What does this mean? We want to make it between around 0, right? So if it's around 0, it's probable. We don't add much penalty. If it's far away from 0, this will be big. We will add penalty, right? I will talk about this in more detail and use the example. Use the iris example in week 8 because this is very important. You have to understand the theory, and you also have to connect this theory to the practical parameter tuning. So then you really know what's the machine learning. And this algorithm doesn't matter. Sometimes some researchers just have an idea, they use a lot of mathematics, and they come up with them. So now go back to this form. Normally, how we can use this form for connect this form to the overfitting and underfitting regularization? Look at this. Parameter. This is parameter. So this is what you want to do. Actually, it's just regularization. And what this? This is care about, I want to make this sign is a positive example, make that sign is negative example. This care about the the fit to the training data, but it's still useless. This is fixed. It's fixed in your algorithm. You can't change that. So there is no hyperparameter for you to change. So it could help you. Now I will introduce another thing here to help you do regularization. Let's think about one case. If we have an outlier like we have outlier like to put the positive sample here. This line will be totally changed because of this, right? It may be changed to something like this. So now the data, just the model on generalized will, because if you make according to this, you maybe make a line, like this. You know, this line is worse because here we have some group of positive example. If we have new example, it can be misclassified. So we want to avoid this. We don't want, if this is training data, we want to give a penalty to this. How we can give the penalty to this? Of how we can just make a relaxation on fit to this data point. So I will put the constraint by the yi times wxi transpose plus b less than 1. So what you want to do is look at this line. I said I don't need to be less than -1. I can say, okay, don't need to be -1. How about just -0, 2, -3? I also accept this. So now you own fit your models. This is model. You own fit your model towards this point, okay? So how you do that? Add a positive term here. So this positive term will, just take the example here. If you add that positive term here, it's actually equal to make this smaller. You don't need to make this 1. Maybe this is hard to understand. Take this form to understand it. If you say here, I have an example here. This is outlier. How you can avoid your model to fit to this outlier? You do some relaxation. You don't want to say, okay, this is W transpose X plus B equal to 1. I don't need to be equal to 1. I can make it maybe find, just say if it's less than 0.2, it's okay. So I can find another line, maybe just here. That's okay. I make some relaxation for this because it's a real outlier, something like this. So you add this term here. So clear? Because you move this this boundary according to these extreme examples by adding this. So now, if you have this constraint rather than the original this one, you have to, oh, okay, I still miss another constraint. You have to make sure it's large than 0. So then what's the final objective become? I think here -1. I don't find a place to. Let me have a look at my notes. Kernel softmax, then you do this. Actually, it's like minimize has minimized this thing. I don't think you need the absolute because it's yep. You just minimize this. Okay. So now you can have a parameter to 10 to change for regularization. Is this? This actually corresponds to the C. If you have using sklearn SVC, you have a parameter called C. What's C? If you make C, you can see as the inverse of a lambda. I'm not sure the precise formula between lambda and C, but I'm sure it's in a relation of it's inverse relation. Something like you have lambda C equal to 1 over lambda, something like this. So if you make C bigger, what do you mean? If you make C smaller, actually this will be bigger, this will be bigger. That means you put more weight on this regularization terms. You put more relaxation, focus on the relaxation. So you will get more. You will get more regularization. Oh, good. No good. That's okay. Just remember this. Just remember, if you get C bigger, that means you make this smaller. If you make it smaller, you have less penalty. If you have less penalty, what's that?
The function is
The model will what?
higher accuracy
On which? On what?
on the prediction.
On test data of training data. Sorry?
I don't know.
If you have more penalty, that means you focus on you make more relaxation for the training data. You don't want to focus on the specific training data. That means if you train this line maybe not cannot correctly predict this line. This is a law. How it's a law? If this is larger than if this is larger than 1, if this is larger than 1, you will 1 minus something larger than 1. It will be negative, right? It would, if it's negative, that means this boundary will just below this 1, right? So, but your model is this boundary. So actually, according to this boundary, your training data is misclassified. So that means the accuracy on the training data will be worse. Okay? More penalty. That means you allowed misclassification on training data. That means your accuracy on training data will decrease. You will avoid overfitting. Overfitting means you overfit training data. So why we want to avoid that? Why?
Because we want it more accuracy on test data, not training.
Yep, that's a true thing. So, but is it always good? Is it you always want to avoid? You want to make this maybe a little bit bigger so we can kind of avoid overfitting? Is this always is always required? You have to ensure the original model is overfitting without this term. If this term, without this term of this penalty is very small, maybe if 0.2 is very small, lambda is small, is less penalty, then you look at your training data, accuracy on training data, oh, very big. Accuracy on test data, oh, very small. Then you know it overfit to training data. Then you can say, okay, if I don't add this regularization term, I want to add it now. If you add it, you need to increase it to make more penalty, okay? Make sense? Yeah, that's it. Of course, this is a penalty for the SVM. In logistic regression, the penalty still. In logistic regression, what's the penalty term? What's the parameter for penalty? I think we still specify it. What's that? I think it's also called, in sklearn, it's also have a parameter called some lambda or something like that. You use L1, L2, right? You say L1, L2. Do you set lambda for L1 and L2?
It's penalty.
Sorry?
It's penalty.
It's penalty?
It is penalty. So the parameter is penalty also.
You
Yeah.
mean it's called penalty?
Yeah.
But you should, this penalty also just allow you to say L2 and L1.
Equal to
Yeah, but still, it has similar thing like that. Let me show you. Let me go back to, okay, now support vector machine is done. Don't focus on support vector machine. Now go back to the logistic regression and the linear regression. We want to, want to minimize, if for linear regression, you know, is the square, something like this. If classification logistic regression, we have like log y minus plus minus here. Y minus y log y minus y height. Something like this. We have this. So L1, what's L1? We have bet 1 here. This is L1, right? You say, okay, it's L1, it's like this. If you say it's L2, it's something like this. But we still have something called lambda to control the how many magnitude of this. So if you search on sklearn linear regression parameters, you should find something called lambda. That's it. Let me have a look now. Linear regression. Lambda in linear regression sklearn. Let me ask ChatGPT for regularization. Oh, what's that? Linear regression sklearn regularization typical lambda so L1, L2 elastic is how lambda. Okay. It's, you know, that's why I hate, you know, this library is too high level. It's like if you use sklearn, it has collinear model. Then you have something called ridge. Then in ridge, it has something called alpha. This alpha is for the lambda. Do you know what's ridge? It's a linear regression for L2 over L1. Yeah, it's L2. You know, ridge is something like this. So for L1, we call it lasso. You know, lasso is like a line. So you know, L1 is like a line because the form is beta 1. But for L2, the form is beta 1 square. Square is like you have some curve. Yeah, that's it. You know, that's why I hate it. It's just one algorithm. We just add something there, then it become, you have this fancy name like Ridge, you have fancy name like Naso. Then you will be confused with a lot of terminology. Then you expand the machine learning algorithm to some other people. You will use a lot of terminology, but you don't know what's the connection between them. Oh, that's it for today. So the rest of time we'll discuss some